Welcome to Sleepy Systems. Tonight, we're exploring why skyscrapers don't collapse during massive earthquakes and the hidden systems keeping entire cities standing. Leave a comment telling me where you're watching from, and do you know any famous skyscrapers or buildings that collapsed because of earthquakes? Don't forget to subscribe, leave a like, and thank you so much for your support. At first, the movement almost never looks dangerous. In videos recorded during major earthquakes, the ground itself often appears strangely calm. Cars may shake slightly, streetlights sway, a few windows rattle. But then the camera tilts upward toward the skyline, and suddenly the illusion breaks apart. Entire skyscrapers begin moving from side to side in long, slow waves that seem physically impossible, as if hundreds of thousands of tons of steel and concrete have somehow turned soft. In Tokyo, office towers have been filmed bending so far that people inside believed the glass would burst outward at any second. In Mexico City, buildings have appeared to rock back and forth like ships trapped in rough ocean water. And yet many of them survive. That is the part that unsettles engineers the most. Not that buildings move during earthquakes, but that they move so much without collapsing. Because the real danger of an earthquake is not always the shaking people feel beneath their feet. It is the invisible transfer of energy moving upward through the structure itself. A skyscraper does not fail because the earth simply shakes too hard. In many cases, the collapse begins because different parts of the building stop agreeing on where the ground actually is. The lower floors may already be moving east, while the upper floors are still trying to move west. Columns twist, beams stretch, glass flexes. Every floor develops its own delay, its own rhythm, almost like separate layers of the building are briefly living in different moments of time. And for a few seconds, one of the largest structures humans can build starts behaving less like a solid object and more like a living system struggling to stay balanced. That strange transformation begins with a force most people never see directly. Deep underground, massive sections of Earth's crust are constantly under pressure. Tectonic plates move only a few centimeters each year, but the rocks along fault lines often refuse to slide smoothly. They lock together for decades, sometimes centuries, storing enormous stress. When the pressure finally exceeds the strength of the rock, the fault ruptures almost instantly. The release sends waves of energy outward through the ground in every direction. Some waves push the earth up and down. Others move it side to side. Some travel quickly through deep rock layers, while others slow down and grow stronger near the surface. By the time these waves reach a city, they have become something incredibly chaotic. The ground beneath one corner of a building may already be shifting, while the opposite side has not moved yet. In extremely large earthquakes, entire sections of land can slide several feet in only moments. But even then, the movement itself is often smaller than people imagine. In many cases, the ground may only shift a short distance horizontally. The real problem is acceleration. Earthquakes force the ground to change direction violently and repeatedly, and buildings resist that motion because of inertia. A skyscraper wants to remain still, even while the earth beneath it is moving. That resistance creates stress throughout the structure. The taller the building becomes, the stranger this effect grows. The upper floors lag behind the lower ones, causing the entire tower to sway. Some skyscrapers can move several feet during major earthquakes without failing. To people inside, this feels terrifyingly unnatural because human intuition expects massive structures to behave rigidly. But rigidity is often exactly what makes buildings dangerous. One of the most misunderstood ideas about earthquake engineering is the belief that strong buildings should remain perfectly still. In reality, many modern skyscrapers are intentionally designed to move. Engineers discovered long ago that a completely rigid structure absorbs earthquake forces directly into its frame. Instead of bending, it cracks. Instead of swaying, it snaps. Nature quietly demonstrates this principle everywhere. During storms, stiff trees often break, while flexible trees survive by bending with the wind. Earthquake-resistant buildings operate under a surprisingly similar philosophy. The goal is not to eliminate motion. The goal is to control it. But controlling movement becomes far more complicated because every structure has something called a natural frequency. Every object on Earth has one. A wine glass vibrates at a certain frequency. A bridge does too. So does a skyscraper. If outside forces begin matching that frequency, the movement can grow dramatically larger through resonance. This is where earthquakes become deeply unpredictable. Sometimes, a building survives an enormous earthquake with minor damage, while another building nearby collapses during a weaker event. The difference may have less to do with strength and more to do with timing. If the frequency of seismic waves matches the natural rhythm of the structure, the building can begin amplifying its own motion. Each sway adds energy into the next one. Engineers have compared this to pushing someone on a swing. Small pushes become powerful if they arrive at exactly the right moment. One of the clearest examples happened during the 1985 Mexico City earthquake. The epicenter was more than 200 miles away near the Pacific coast, yet some of the worst destruction occurred inside Mexico City itself. Entire buildings collapsed, while others nearby remained standing. What made the disaster especially puzzling was that many damaged structures were between 6 and 15 stories tall. Scientists later realized that the ancient lake bed beneath the city had amplified seismic waves at frequencies matching buildings of similar height. The soft soil acted almost like a giant bowl of gelatin, trapping and strengthening the motion. In some neighborhoods, the ground moved far more violently than surrounding regions built on harder rock. The earthquake exposed something unsettling about modern cities. A building is not only interacting with the earthquake, it is also interacting with the ground beneath it, the nearby structures around it, and even its own internal rhythm. In some ways, every skyscraper enters a negotiation with the earth during a major quake, and the outcome depends on countless invisible variables happening simultaneously. This may explain why earthquake engineering still contains elements of uncertainty despite decades of research. Engineers can model enormous amounts of data, but real earthquakes rarely behave perfectly according to expectations. Some seismic waves bounce unpredictably through underground geology. Others combine in strange ways scientists still study today. Certain buildings experience torsion, where one side twists more violently than the other because the mass is unevenly distributed. In older structures, weak floors can suddenly collapse and transfer crushing loads downward in seconds. Meanwhile, neighboring buildings sometimes slam into each other during intense shaking if they sway out of sync. In dense cities, this creates a disturbing possibility where one unstable structure can indirectly damage another beside it. Yet, despite all this complexity, many skyscrapers survive astonishingly well. The reason lies partly in how modern buildings distribute force. Contrary to popular belief, skyscrapers are not solid blocks. Most behave more like carefully balanced skeletons. Steel beams stretch slightly under pressure. Concrete cores absorb movement. Connections between structural elements are designed to deform without instantly breaking apart. During severe shaking, parts of a building may even suffer controlled damage intentionally. Certain joints are expected to crack first, so the main structure can survive longer. This idea can feel counterintuitive because damage usually sounds like failure, but in earthquake engineering, tiny sacrifices often prevent catastrophic collapse. Some structures are designed almost like shock absorbers in a car, allowing movement to dissipate energy gradually rather than concentrating it all at once. Japan became one of the world's leading laboratories for these ideas after repeated destructive earthquakes forced engineers to rethink nearly every assumption about tall buildings. In Tokyo today, many skyscrapers appear calm from the outside during moderate quakes, even while hidden systems inside them are constantly adjusting. Dampers filled with fluid slow motion between floors. Massive steel braces redirect stress through different pathways. Some towers contain enormous counterweights suspended near the top that swing opposite the building's movement to reduce swaying. To outsiders, these systems can feel almost surreal, as though modern buildings are quietly fighting gravity and earthquakes at the same time. Yet none of these technologies make structures invincible. Engineers often describe earthquake-resistant design as a matter of probability rather than certainty. Buildings are created to survive expected levels of shaking based on historical data and geological models. But nature does not always respect those limits. Extremely rare earthquakes can exceed predictions. Soil conditions may behave differently than simulations suggested. Construction shortcuts, aging materials, or hidden weaknesses can suddenly matter at the worst possible moment. Some experts argue that no building is truly earthquake-proof. The phrase itself may be misleading. Many structures are simply designed to avoid collapse long enough for people to escape. And perhaps that is what makes skyscrapers during earthquakes feel so psychologically unsettling. They reveal how much modern civilization depends on controlled flexibility rather than absolute strength. From a distance, tall buildings appear permanent, rigid, almost immovable. But under seismic stress, they survive precisely because they stop acting rigid. They bend, they sway, they absorb damage. They negotiate with forces far larger than themselves. And hidden inside that movement is a strange reality most people never think about while standing beneath a skyline at night. Some of the tallest structures humans have ever created remain standing not because they resist the Earth completely, but because they have learned, in carefully calculated ways, how to move with it. For most of human history, strength meant rigidity. The logic felt obvious. Thick castle walls survived attacks because they were solid. Stone temples lasted thousands of years because they barely moved. Massive structures inspired confidence precisely because they looked incapable of bending. Even today, people standing beneath a skyscraper instinctively trust buildings that appear heavy, dense, and immovable. But earthquakes quietly expose a flaw in that intuition. In the modern world, some of the most dangerous buildings during seismic events are not the weakest looking ones. They are often the ones that resist movement too aggressively. And that realization changed architecture forever. One of the strangest things about major earthquakes is that destruction rarely spreads evenly through a city. Some buildings crack but survive. Others collapse suddenly with terrifying speed. Sometimes, two nearly identical structures sitting blocks apart experience completely different outcomes. Engineers studying these failures eventually discovered something unsettling hiding beneath the surface of modern construction. A building does not survive because it refuses to move. In many cases, survival depends on how well it can surrender to movement without falling apart. That idea sounds almost contradictory at first. Humans associate flexibility with weakness, but nature repeatedly suggests otherwise. During hurricanes, rigid trees often snap, while flexible trees bend and recover. Human bones themselves contain slight elasticity because perfectly brittle bones would shatter constantly under stress. Even bridges are built to sway slightly in the wind. Absolute stiffness creates a hidden problem. It leaves nowhere for energy to go. Earthquakes force buildings into sudden motion, and every part of a structure reacts depending on its weight, shape, materials, and timing. If a building is too rigid, the seismic energy travels directly into its frame instead of dispersing gradually. Pressure begins concentrating at weak points. Tiny fractures form inside concrete. Steel connections experience extreme stress. The structure may appear stable from the outside, while dangerous internal damage spreads invisibly through the skeleton beneath the walls. Some engineers compare this process to snapping dry pasta. A stiff object tolerates pressure until suddenly it doesn't. There is little warning between stability and catastrophic failure. This became painfully clear during many early 20th century earthquakes when masonry buildings collapsed with shocking violence. Unreinforced brick and stone structures were especially vulnerable because they possessed enormous compressive strength but very little flexibility. Stone can support tremendous weight pushing downward. Ancient Roman aqueducts and cathedrals proved that centuries ago. But earthquakes introduce sideways motion, and sideways motion changes everything. When rigid masonry walls begin moving laterally, cracks can spread rapidly through the structure because the material cannot stretch enough to absorb the energy. Entire sections may separate and collapse outward into streets within seconds. This pattern appeared repeatedly during earthquakes in Italy, Turkey, and parts of Latin America where older masonry construction remained common. In some historic cities, centuries-old churches survived wars, storms, and time itself, only to collapse during moments of violent seismic movement, lasting less than a minute. Yet, even modern concrete buildings revealed similar vulnerabilities under certain conditions. Reinforced concrete transformed architecture because steel bars embedded inside concrete helped structures resist tension and bending forces more effectively. But concrete still contains a dangerous contradiction. It performs extremely well under compression, yet remains comparatively brittle under repeated flexing. During severe earthquakes, sections of reinforced concrete can begin cracking internally long before visible failure occurs. If the shaking continues, those cracks may expand faster than engineers anticipated. Some of the deadliest collapses in history involved reinforced concrete structures that appeared modern and strong, but lacked sufficient ductility. Ductility became one of the most important concepts in earthquake engineering, though most people outside the field rarely hear the term. It refers to a material or structure's ability to deform without suddenly breaking apart. In practical terms, ductility means a building can bend, twist, or absorb damage gradually while remaining standing long enough to protect human life. This changed the philosophy of structural design in profound ways. Engineers slowly realized that the safest building during an earthquake might not be the strongest in the traditional sense. It might be the one capable of controlled weakness. That distinction sounds subtle, but completely reshaped skyscraper engineering. Instead of trying to make structures perfectly rigid, designers began focusing on how buildings fail under stress. They studied where cracks form first, how energy moves through a frame, and which components could deform sacrificially to protect the rest of the structure. In some cases, engineers intentionally design parts of buildings to absorb damage during major earthquakes. Certain joints may bend permanently. Specific braces might deform under pressure. Sections of the building could require replacement afterward. But if those failures happen in predictable ways, the main structure survives. This philosophy can feel emotionally uncomfortable because people prefer the idea of indestructibility. Yet, modern earthquake engineering often accepts that damage is unavoidable. The goal becomes preventing sudden collapse rather than preventing all harm. Japan demonstrated this principle dramatically after repeated earthquakes forced the country to evolve beyond older assumptions about rigid construction. In the aftermath of devastating seismic events throughout the 20th century, Japanese engineers began embracing designs that treated movement not as an enemy, but as something to manage carefully. Some buildings appeared almost unsettling during tests, swaying far more than ordinary people considered safe. Yet that movement reduced stress inside the structure itself. The building survived precisely because it was allowed to flex. Watching footage of earthquake simulations in Japanese testing facilities can feel strangely counterintuitive. Towers shake violently while remaining intact. Floors shift side to side. walls flex visibly. To an untrained observer, the movement looks catastrophic. But engineers often view controlled motion as evidence the system is functioning correctly. The building is releasing energy instead of trapping it. That shift in thinking also transformed how skyscrapers were constructed in places like California, Taiwan, and New Zealand. Flexible steel frames became increasingly important because steel behaves differently from rigid masonry or brittle concrete alone. Steel can stretch slightly under stress and return toward its original shape without immediately fracturing. This elasticity gives structures more time to absorb seismic forces. But even steel introduces trade-offs. Buildings that flex too much can create terrifying motion for occupants, damage internal systems, or collide with neighboring structures. Engineers, therefore, entered an ongoing balancing act between flexibility and control. Too rigid becomes brittle. Too flexible becomes unstable. Somewhere between those extremes lies survivable motion. And that balance grows more complicated as buildings become taller. Height changes how forces move through a structure. A low-rise building may experience quick, violent shaking. A skyscraper often develops slower, rolling movements that can continue long after the earthquake waves pass through the ground below. In extremely tall towers, the upper floors may sway several feet in each direction. People inside sometimes report nausea or disorientation because the motion feels almost ocean-like. During the 2011 Tohoku earthquake in Japan, some skyscrapers in Tokyo continued swaying for many minutes despite being hundreds of miles from the epicenter. Long-period seismic waves traveled enormous distances and interacted strongly with tall structures. This revealed another unsettling truth. Modern skyscrapers are not merely resisting earthquakes, they are participating in them. Every building modifies how seismic energy moves through itself. Some experts even describe cities as giant collections of interacting oscillators, each structure responding differently depending on height, weight, materials, and ground conditions. In dense urban environments, this creates incredibly complex behavior that researchers still study today. Certain frequencies may affect mid-rise buildings more severely, while others target taller towers. Soil composition can amplify some vibrations and dampen others. In rare cases, neighboring buildings may even influence one another's motion indirectly through shared ground response. These discoveries gradually pushed engineers away from simplistic ideas about stronger equals safer. Strength alone could not explain survival. Adaptability mattered just as much. There is something philosophically strange about that conclusion, because it mirrors patterns seen repeatedly in natural systems. Species that survive environmental change are often not the strongest or fastest, but the most adaptable. Materials that endure repeated stress usually possess some ability to flex. Even the Earth's crust itself releases pressure through movement, rather than remaining perfectly rigid forever. Some engineers quietly argue that earthquakes reveal a broader truth about civilization itself. Human structures appear permanent only because movement is usually too slow for us to notice. Cities feel stable because geological time moves differently from human time. But deep underground, the planet is constantly shifting, bending, grinding, and storing energy beneath every skyline humans build. Earthquakes briefly expose that hidden instability, and perhaps that is why watching skyscrapers sway feels psychologically disturbing, even when they survive. The movement breaks the illusion of permanence. It reminds people that modern cities are not fixed against nature, but suspended within it, relying on carefully calculated flexibility to remain standing at all. In the end, earthquake-resistant buildings do something deeply unintuitive. They survive not by behaving like immovable monuments, but by behaving more like living systems, absorbing stress, adapting under pressure, and yielding just enough to avoid breaking completely. And once engineers accepted that idea, an even stranger possibility emerged. If a building could survive by moving with an earthquake instead of resisting it, then perhaps the safest skyscrapers of the future would not be anchored rigidly to the ground at all. From the outside, skyscrapers look deceptively simple. Glass, steel, concrete, straight lines disappearing into the sky. But hidden beneath that clean appearance is one of the strangest engineering ideas modern civilization has ever accepted. Some of the safest buildings on Earth are designed to bend, not metaphorically, physically. During a powerful earthquake, certain skyscrapers can sway several feet in each direction without collapsing, and the people inside may never realize how close the structure comes to the limits of what physics allows. The first time many engineers truly understood this was not during a successful experiment, but during failure. Throughout the 20th century, earthquakes repeatedly exposed a brutal pattern. Buildings that appeared massive and permanent sometimes cracked apart with shocking speed, while other structures nearby survived despite looking lighter or less imposing. Over time, researchers began noticing that survival often depended less on the amount of material used and more on how forces traveled through the building itself. That realization changed architecture from the inside out. A modern skyscraper is no longer treated like a giant stone tower resisting nature through sheer weight. It behaves more like a carefully balanced system of moving parts, constantly redistributing stress, redirecting pressure, and deciding in fractions of a second where energy should go next. In many ways, tall buildings today resemble enormous mechanical organisms hidden beneath layers of glass. The illusion begins with the walls themselves. Most people instinctively assume the outer walls of a skyscraper hold the building up. Historically, that was true. Ancient structures relied heavily on thick, load-bearing walls to support weight. The taller humans tried to build, the thicker the lower walls had to become. Some early skyscrapers in the late 19th century required absurd amounts of masonry at their base just to remain stable. But that system had limits. Eventually, walls became so thick they consumed valuable space and still struggled under extreme stress. The breakthrough came when engineers stopped thinking of buildings as stacked stone boxes and started treating them like skeletal frames. Steel transformed everything. Instead of relying on exterior walls, skyscrapers began using internal frameworks made of interconnected columns and beams. The building's weight traveled through this hidden skeleton down into the foundation below. Suddenly, walls no longer needed to carry most of the load. They could become thinner, lighter, and covered in glass. But this also created a new possibility during earthquakes. A steel skeleton could flex. That flexibility became one of the defining secrets of earthquake-resistant design. During seismic motion, the frame absorbs and redistributes energy across the structure, rather than allowing stress to concentrate instantly in one location. But the details of how this happens are surprisingly complex. Inside many skyscrapers, enormous vertical columns act almost like the bones of the building, carrying gravity loads downward. Horizontal beams connect those columns across every floor. Together, they form a giant, three-dimensional grid. During an earthquake, however, gravity is not the primary threat. Sideways motion becomes the real danger. When the ground shifts laterally, the entire frame wants to deform. Without additional systems, the building could begin leaning or twisting uncontrollably. That is why many skyscrapers rely on special structural components designed specifically for lateral forces. One of the most important is something engineers call a shear wall. Shear walls are incredibly strong vertical sections, often built around elevator shafts or stairwells near the building's center. These walls act almost like the spine of the structure, resisting horizontal movement and helping the tower maintain its shape while the surrounding frame flexes around it. During severe earthquakes, enormous forces travel into these central cores. In some skyscrapers, the concrete walls near the core are several feet thick because they must absorb tremendous stress without failing. Yet even these walls are not expected to remain perfectly rigid. Small movements are anticipated. Tiny cracks may form. Controlled deformation becomes part of the survival strategy. Another strange feature appears in buildings using cross-bracing systems. These diagonal steel braces often form giant X shapes hidden inside walls or visible across parts of the structure. To outsiders, they may seem decorative or unnecessary. But during earthquakes, these braces help redirect forces throughout the building, like tension cables inside a suspension bridge. Instead of allowing floors to shift independently, the braces tie sections together so the motion spreads more evenly across the frame. Some engineers describe this process almost like guiding water through channels. The goal is not stopping energy completely, it is controlling where the energy flows. Because uncontrolled force is what destroys structures. This is where skyscraper design starts becoming almost philosophical. Engineers learned that earthquakes cannot truly be defeated. The energy released by large tectonic events is simply too enormous. A major earthquake may release more energy than multiple nuclear bombs. No building can completely overpower that kind of force through brute strength alone. So modern earthquake engineering became less about resistance and more about negotiation. Buildings survive by cooperating with physics in carefully calculated ways, and nowhere is that more visible than in moment frame systems. Moment frames are special beam and column connections designed to bend without breaking apart. During strong shaking, The joints between steel beams and columns can rotate slightly while remaining connected. That tiny rotational movement allows the structure to dissipate energy gradually instead of concentrating it all into brittle fractures. Watching slow-motion footage of earthquake tests on these systems feels almost unsettling because the buildings appear alive. Floors sway, steel bends visibly, entire frames distort and then partially recover. To people unfamiliar with the science, it looks like failure. Yet the movement itself is often evidence the structure is working exactly as intended. The building is sacrificing rigidity to preserve integrity. Some of the most revealing insights came after the 1994 Northridge earthquake in California. Engineers initially believed many welded steel moment frames were highly resilient. But after the quake, inspectors discovered unexpected fractures inside supposedly strong connections. Some cracks were hidden beneath layers of fireproofing and remained invisible from the outside. This shocked the engineering community because it revealed how complicated real earthquake behavior could become. Structures did not always fail where models predicted. Tiny weaknesses in welds could matter enormously under repeated stress. As a result, building codes and connection designs changed significantly afterward. The earthquake became another reminder that skyscrapers are not static objects. They are dynamic systems filled with countless interacting variables. And perhaps the most unsettling variable is torsion. Torsion occurs when different parts of a building move unevenly, causing the structure to twist during shaking. This often happens when a building's mass is distributed asymmetrically. Imagine grabbing a tall object at one corner and shaking it sideways. Instead of moving cleanly in one direction, it rotates. Earthquakes can create similar effects on entire skyscrapers. One side may experience stronger forces than the other, depending on geometry, ground conditions, or structural layout. Twisting introduces highly unpredictable stresses that can damage columns, beams, and connections in dangerous ways. That is why many modern towers are designed with remarkable attention to symmetry and balance. Even subtle irregularities can matter during extreme seismic motion. Some researchers believe torsional instability contributed to certain collapses during historical earthquakes, though the exact mechanisms are sometimes debated. In dense cities, another strange phenomenon occasionally emerges. Tall buildings may influence each other indirectly through the ground beneath them. During large earthquakes, seismic waves interact with soil layers in highly complicated patterns. Some scientists have explored whether clusters of skyscrapers can modify local vibration behavior in ways not fully understood yet. The idea remains an active area of research, but it reflects how earthquake engineering increasingly views cities not as isolated buildings, but as interconnected systems sharing energy during seismic events. A skyscraper no longer exists alone. It becomes part of a larger mechanical landscape, responding collectively to the Earth's movement. Yet, despite all this complexity, perhaps the most important realization is surprisingly simple. The true strength of many modern buildings lies not in the materials themselves, but in the relationships between them. Connections matter more than appearances. A skyscraper's survival often depends on thousands of joints, welds, braces, and transitions working together under stress. If forces move smoothly through the structure, the building can endure astonishing motion. But if energy becomes trapped or concentrated suddenly, even strong materials may fail. This changes how skyscrapers should be imagined entirely. They are not giant blocks stacked toward the sky. They are flexible networks constantly balancing gravity, motion, and internal tension. And during earthquakes, those hidden systems reveal themselves for a few terrifying moments. Glass ripples, floors sway, steel groans deep inside the walls where no one can see it. The tower bends just enough to survive. And maybe that is the strangest part of all. The skyscrapers people trust most are often the ones quietly moving around them every day, flexing invisibly against wind, gravity, temperature, and the shifting planet beneath their feet. But eventually, engineers began asking an even more radical question. If buildings survive because they can bend, what would happen if the building could partially disconnect itself from the earthquake altogether? For centuries, humans treated buildings as extensions of the ground itself. A structure rose upward from its foundation, locked tightly into the earth beneath it, as if stability depended attachment. That idea feels so natural, most people never question it. Of course, buildings should be firmly anchored. Of course, the safest structure would grip the ground as tightly as possible. But earthquakes slowly forced engineers toward a far stranger conclusion. What if the ground itself is the problem? What if the most dangerous thing a building can do during an earthquake is stay fully connected to the earth beneath it? That question led to one of the most unusual technologies hidden beneath modern cities today. In certain buildings, especially in Japan, California, and New Zealand, the structure above is not completely fixed to the ground below. Instead, massive systems buried beneath the foundation allow the building to move separately from the earthquake itself. To people standing inside, the effect can feel almost impossible. The earth may shake violently while the building above moves slowly and calmly, as if floating slightly out of sync with reality. Engineers call this base isolation, but the phrase barely captures how strange the concept truly is. Because in practical terms, some buildings survive earthquakes by partially disconnecting themselves from the planet. The idea emerged from a simple but unsettling observation. During earthquakes, many structures do not fail because they are weak in isolation. They fail because seismic energy transfers directly upward from the moving ground into the frame. Every violent shift of the earth becomes a violent shift inside the building. Floors accelerate, columns bend, walls absorb enormous stress. Even well-designed skyscrapers experience dangerous forces because the foundation faithfully copies the movement happening underground. Traditional earthquake engineering focused heavily on helping buildings endure that energy once it entered the structure. Base isolation approached the problem differently. Instead of strengthening the building against seismic motion, engineers began asking whether the motion could be interrupted before it reached the structure at all. The result looks deceptively simple on paper. Between the foundation and the building itself, engineers place flexible isolation systems designed to absorb or redirect movement. But beneath that simplicity lies decades of experimentation, physics, and risk. One common design uses enormous layered bearings made of steel and rubber. These devices can be several feet wide and are installed underneath the building at key support points. Under normal conditions, the structure above remains stable and perfectly functional. But during an earthquake, the isolators flex sideways while supporting the weight of the building. The ground moves sharply. The building moves more gradually. Instead of transferring violent acceleration directly upward, the isolation system stretches the motion over time, reducing the forces entering the structure above. To visualize this, engineers sometimes compare it to standing in a subway train. If the train stops suddenly while your feet are locked rigidly in place, your body experiences an abrupt jolt. But if your knees bend and absorb some of the motion, the force spreading through your body decreases. Base isolation applies a similar principle to entire buildings weighing thousands or even millions of tons. The building is allowed to ride the earthquake instead of fighting it directly. Yet, the deeper engineers explored this concept, the stranger it became. Some isolation systems do not merely flex, they slide. Certain buildings rest on curved bearings that allow the structure to move horizontally during seismic shaking, almost like a giant pendulum. These systems are carefully engineered, so gravity naturally helps pull the building back toward its original position afterward. During major earthquakes, the entire structure may shift several inches or even feet relative to the ground below. Hidden beneath hospitals, museums, and government facilities, gigantic mechanical components quietly absorb movements powerful enough to destroy conventional buildings. And most people walking through these structures never realize they are standing above systems specifically designed to let the earth move without fully taking the building with it. Japan became one of the most important proving grounds for this technology because few places on Earth experience earthquakes as frequently or intensely. In Tokyo, Osaka, and other dense urban regions, engineers faced a terrifying reality. Some critical structures simply could not afford catastrophic failure. Hospitals needed to remain operational after major quakes. Emergency centers had to function during disasters rather than after them. Traditional structural reinforcement alone was not always enough. Base isolation offered a different path. Over time, some Japanese buildings equipped with advanced isolation systems performed remarkably well during severe earthquakes. In certain cases, occupants inside isolated structures reported surprisingly gentle motion, even while nearby areas experienced violent shaking. Footage from earthquake simulations in Japanese testing facilities can feel almost surreal. The ground platform beneath the building jerks violently from side to side, while the structure above glides more slowly, almost peacefully, as though separated from the chaos underneath. Watching it creates a strange psychological effect because the building appears calm, while the earth itself behaves unpredictably. It reverses the instinctive relationship humans expect between architecture and the ground. Yet, base isolation is not magic, and engineers are careful about oversimplifying its capabilities. The systems work best under certain conditions and face important limitations. Some isolation designs are extremely effective against horizontal motion, but less helpful against vertical acceleration. Others may struggle under exceptionally large displacements if the ground moves farther than anticipated. Soil conditions matter enormously. Long-duration shaking introduces additional complexity. Engineers must also consider what happens to utilities connected to the structure. Water pipes, electrical systems, gas lines, and communication cables all need flexibility because the isolated building can move independently from the surrounding ground. In some designs, special joints and flexible connectors allow infrastructure to shift safely during earthquakes. Without those accommodations, the building itself might survive while critical systems rupture underneath it. This reveals another hidden truth about earthquake engineering. A building is never truly isolated from the larger systems around it. Cities function through networks of interconnected infrastructure, and seismic resilience depends on far more than the survival of individual towers. Some researchers even argue that future earthquake-resistant cities may require entirely new approaches to urban flexibility, not just stronger structures. Another fascinating aspect of base isolation is how it changes the emotional experience of earthquakes inside buildings. Traditional skyscrapers often amplify certain frequencies of motion as energy moves upward through the frame. Occupants may feel dramatic swaying or violent shaking, depending on the building's design and the nature of the earthquake. Isolated buildings frequently behave differently. Instead of sharp jolts, people sometimes report slower, rolling motion. The earthquake feels distant somehow, softened. This creates an eerie disconnect because the destruction outside may still be severe. In some cases, isolated hospitals remained operational after nearby structures suffered significant damage. Museums housing priceless artifacts adopted isolation systems to protect collections impossible to replace. One remarkable example is the San Francisco City Hall retrofit, completed in the early 2000s. Engineers installed hundreds of base isolators beneath the historic structure, while preserving the building above. During future earthquakes, the massive City Hall would be capable of moving independently from the ground beneath it. The image itself feels almost paradoxical. A century-old government building resting atop giant mechanical cushions designed to let it slide during seismic chaos. Similar technologies now protect airports, data centers, laboratories, and emergency facilities around the world. Yet, the deeper scientists study earthquakes, the more complicated the problem becomes. Some seismic waves behave unpredictably, depending on local geology. Certain soil layers amplify low-frequency vibrations in ways difficult to model perfectly. Near-fault earthquakes can produce intense pulses of motion that challenge existing assumptions. Researchers continue debating how different isolation systems perform under rare but extreme scenarios. There is also the uncomfortable reality of cost. Base isolation can significantly increase construction expenses, especially for very large or highly specialized buildings. As a result, many ordinary structures around the world still rely on more conventional seismic design. This creates an uneven landscape where some buildings possess extraordinary earthquake defenses while others remain vulnerable. In rapidly growing cities near active fault zones, the gap between engineering capability and economic reality remains enormous. And perhaps that tension reveals something deeper about modern civilization itself. Earthquake-resistant technology has become increasingly sophisticated, almost futuristic at times. Humans have developed buildings capable of bending, sliding, swaying, and partially disconnecting themselves from the moving earth below. But all of these systems ultimately exist because the planet remains fundamentally unpredictable beneath us. The ground under every city is not truly stable. It only appears stable because human lives are short compared to geological time. Deep underground, pressure continues accumulating silently beneath coastlines, mountains, and fault systems all over the world. Base isolation does not eliminate that danger. It simply buys time by changing the conversation between buildings and earthquakes. Instead of absorbing every violent motion directly, the structure negotiates with the earth more carefully, filtering chaos before it rises upward into the tower above. And as engineers refined these systems, another strange realization emerged. Even after reducing the energy entering a skyscraper, tall buildings still faced a dangerous problem high above the ground. Because once towers reached extreme heights, they no longer needed earthquakes alone to start moving. Sometimes the wind itself became enough. And to control that motion, engineers would eventually place something enormous inside the buildings themselves. Hidden machines designed to swing against the movement of the tower, like giant artificial counterweights suspended in the sky. Near the top of one of the tallest skyscrapers on Earth hangs a giant metal sphere weighing more than 700 tons. Tourists visiting the upper levels of Taipei 101 sometimes stop in confusion when they first see it. The object looks less like part of a building and more like something pulled from an industrial science fiction film. An enormous golden ball suspended by thick steel cables between multiple floors high above the city. At first glance, it almost feels absurd. Why would engineers place a massive swinging weight inside a skyscraper already struggling against gravity, wind, and earthquakes? But hidden inside that strange machine is one of the most important secrets of modern skyscrapers. Because once buildings became tall enough, engineers discovered something deeply unsettling. The greatest threat to a tower was not always collapse. Sometimes the real problem was movement itself. Long before a skyscraper comes close to structural failure, motion can begin affecting the people inside. Elevators stop working properly. Water systems malfunction. Windows creak under pressure. Occupants feel dizzy. Furniture shifts slightly across floors. And during storms or earthquakes, the upper sections of extremely tall buildings may sway far more than most people realize. On windy days, some skyscrapers naturally move several feet from side to side at the top. Usually, the motion happens slowly enough that outsiders never notice. But inside, especially on higher floors, sensitive occupants sometimes feel the building drifting gently beneath them like a ship at sea. In certain towers, people have reported nausea, headaches, or disorientation during periods of strong wind. This created a strange new challenge for engineers. Humanity had learned how to build taller and taller structures, but height introduced an invisible psychological limit. Even if the building remained technically safe, people still needed to feel safe inside it. That problem became more serious because wind behaves differently around skyscrapers than many people imagine. Air flowing past a tall structure does not simply push against it steadily. As wind wraps around the sides of a tower, swirling vortices form behind the building. These spinning currents can alternate from side to side, creating rhythmic forces that pull the structure into oscillation. Engineers call this vortex shedding, but the effect itself feels eerily organic. The wind almost begins playing the building like an instrument. Under the right conditions, even relatively moderate wind can create repeating patterns of motion that gradually amplify the tower's sway. And unlike earthquakes, wind may continue for hours. Some early skyscrapers revealed how uncomfortable this could become. Occupants in tall buildings occasionally reported motion strong enough to make hanging lights sway visibly indoors. In a few famous cases, entire office floors experienced subtle but persistent movement during storms. The buildings themselves remained structurally sound, yet engineers realized something uncomfortable. The future of skyscrapers depended not only on preventing collapse, but on controlling motion so precisely that people barely sensed it at all. This led to one of the strangest engineering solutions ever hidden inside modern architecture: tuned mass dampers. The concept sounds technical, but the underlying idea is surprisingly intuitive. If a building moves in one direction, a massive weight inside the building can move in the opposite direction, helping counteract the motion. In effect, the skyscraper carries its own balancing system high above the city. The most famous example remains the giant sphere inside Taipei 101. Suspended between the 87th and 92nd floors, the damper consists of huge steel plates stacked together into a single pendulum-like mass. When strong winds or earthquakes cause the tower to sway, the sphere begins moving slightly out of phase with the building itself. That opposite movement absorbs part of the energy and reduces the overall motion experienced by the structure. Watching videos of the damper during storms feels almost surreal because the object behaves like a living counterforce hidden inside the skyscraper's body. As the tower moves one way, the giant sphere drifts another, quietly stabilizing one of the tallest buildings on Earth. Yet the deeper engineers explored these systems, the stranger they became. The tuned mass damper is not simply a heavy object hanging in space. It must be tuned with extraordinary precision to match the building's natural frequency. Too much deviation, and the system becomes far less effective. Engineers spent enormous effort studying how towers move under different conditions, so the damper responds correctly at exactly the right moments. In some ways, the relationship resembles two dancers moving together in controlled opposition. Timing matters as much as mass. Certain dampers also contain hydraulic systems or additional devices that dissipate energy through friction or fluid movement. Some skyscrapers even use multiple dampers working together to handle different types of motion simultaneously. The entire system begins feeling less like static architecture and more like a giant machine constantly adjusting itself against invisible forces. One reason this became necessary is because modern skyscrapers are far lighter than many people realize. Older buildings often relied heavily on thick masonry and immense weight for stability, but contemporary towers prioritize efficiency, flexibility, and reduced material loads. Advances in steel, concrete, and structural engineering allowed skyscrapers to become taller while using comparatively lighter frameworks. That flexibility improved seismic performance in many ways, yet it also increased susceptibility to motion from wind and long-period vibrations. The taller and more slender a tower becomes, the more sensitive it may grow to oscillation. Some ultra-tall skyscrapers almost behave like giant vertical cantilevers, extending into turbulent air currents thousands of feet above the ground. And as towers rise higher into the atmosphere, the environment surrounding them changes dramatically. Wind speeds increase with altitude. Airflow patterns become more complex around neighboring buildings. Tiny aerodynamic differences in shape can significantly alter how forces interact with the structure. This explains why many modern skyscrapers have unusual forms. Twisting exteriors, tapered tops, rounded corners, and setbacks are often designed partly to disrupt vortex formation and reduce dangerous oscillations. In other words, some buildings are literally shaped to confuse the wind. Engineers discovered that altering airflow around a tower could reduce rhythmic forces before they grew too large. Yet even these aerodynamic strategies sometimes need additional help. That is where giant dampers continue playing their hidden role high above city skylines. Interestingly, tuned mass dampers are not limited to skyscrapers. Variations of the technology appear in bridges, stadiums, observation towers, and even spacecraft systems. Anywhere large structures experience dangerous oscillations, engineers explore ways to absorb and redistribute motion. Some dampers use liquid sloshing inside tanks rather than giant suspended weights. Others rely on computer-controlled active systems capable of adjusting dynamically in real time. In certain advanced designs, sensors constantly monitor building movement, while automated systems respond almost instantly to changing conditions. The line between architecture and robotics begins blurring quietly inside these structures. Buildings no longer merely resist forces. Increasingly, they react to them. But despite the sophistication of these technologies, nature still retains an unsettling ability to surprise engineers. Earthquakes remain especially difficult because they introduce chaotic, multi-directional forces arriving unpredictably. A damper tuned primarily for wind may help during seismic events, but earthquakes often produce far more complicated motion patterns than steady atmospheric forces. Researchers continue debating how future skyscrapers should balance flexibility, damping, and energy dissipation under increasingly extreme conditions. Climate change has also intensified some discussions about structural resilience, as stronger storms, changing weather patterns, and denser urban skylines alter how buildings experience environmental forces over time. Some experts believe future skyscrapers may rely on entirely adaptive systems, capable of continuously changing their behavior based on real-time data. Others caution that growing technological complexity introduces new vulnerabilities humans may not fully understand yet. Still, there is something psychologically fascinating about the existence of tuned mass dampers themselves. Hidden above crowded streets filled with millions of people, giant mechanical counterweights quietly swing inside skyscrapers every day, correcting movements most occupants never feel. Entire towers subtly drift through the air, while invisible systems struggle to keep them calm. It changes the way cities should be imagined. Skyscrapers are not frozen monuments rising rigidly above civilization. They are dynamic structures, constantly negotiating with gravity, weather, seismic forces, thermal expansion, and their own motion. Even on calm days, buildings move slightly under sunlight, temperature shifts, elevator loads, and changing wind currents. Modern architecture only appears still because human senses are too limited to notice the scale of those adjustments. In reality, many skyscrapers are always in motion. And perhaps that is what makes the giant sphere inside Taipei 101 feel so strangely symbolic. It reveals the hidden truth modern engineering rarely advertises openly. The tallest structures humans build are not stable because they overpower nature completely. They remain standing because they are carefully designed to absorb movement, redirect force, and continuously balance themselves against a world that never truly stops shifting. But despite all these advances, engineers eventually discovered another dangerous weakness lurking much lower in certain buildings. Sometimes the problem was not the top of the tower at all. Sometimes an entire skyscraper could fail because of a single vulnerable floor near the ground. A hidden structural weakness capable of bringing thousands of tons crashing downward in seconds. Sometimes a skyscraper does not collapse because the entire structure fails. Sometimes it collapses because one floor gives up before the others. And when that happens, the destruction can look almost unreal, as if gravity suddenly stopped following normal rules. In videos recorded during major earthquakes, there are moments where multi-story buildings appear stable for several seconds after the shaking begins. Windows remain intact. Upper floors still stand upright. Then, almost instantly, the bottom level folds inward, and the entire structure drops vertically onto itself. Floor after floor crashes downward in a chain reaction, often called a pancake collapse, where the weight of the building overwhelms everything beneath it. To people watching from the outside, it can feel impossible that a single weak point near the ground could destroy thousands of tons of concrete and steel above it. But earthquakes repeatedly reveal the same terrifying reality. A building is only as strong as its weakest floor. Engineers call one of the most dangerous versions of this problem a soft story failure. The phrase sounds strangely harmless, almost technical and forgettable. But behind it lies one of the deadliest structural weaknesses modern cities have ever created. A soft story usually forms when one floor of a building is significantly more flexible or weaker than the floors above it. Most commonly, this happens at ground level. Architects and developers often prefer open first floors because they create space for parking garages, storefronts, hotel lobbies, or large windows. Structurally, however, removing walls and supports from one level changes how forces move through the building during an earthquake. The upper floors may remain relatively stiff and heavily reinforced, while the lower floor becomes comparatively weak. Under normal conditions, this imbalance may not seem dangerous at all. The building stands perfectly upright for years. People shop, park cars, and walk through spacious open lobbies without noticing anything unusual. But during strong seismic motion, the difference in stiffness between floors becomes catastrophic. The upper portion of the structure moves almost like a rigid block, while the weaker floor below absorbs extreme sideways deformation. Columns bend beyond their limits. Connections fracture, and if that level fails suddenly, everything above loses support at once. Some of the clearest examples emerged during the 1994 Northridge earthquake in California. Entire apartment buildings with parking spaces beneath living areas suffered devastating collapses, while neighboring structures survived. In many cases, the open parking level became the fatal weakness. Engineers inspecting the wreckage noticed the same disturbing pattern repeatedly. The lower floor had experienced far greater movement than the stories above it. Once those columns buckled, the upper structure dropped downward almost intact, crushing the weakened level beneath it. Similar failures appeared again in earthquakes across Turkey, Taiwan, and other regions where soft-story buildings remained common. The collapses looked frighteningly efficient, as though the earthquake had discovered the exact point where the building's internal balance could no longer hold. What makes soft-story collapse especially unsettling is how invisible the danger often appears beforehand. Many vulnerable buildings look completely ordinary. Some even appear modern and well-maintained. Unlike obvious structural decay or visible cracks, soft-story weakness can hide quietly inside the design itself. A building may perform perfectly under gravity loads for decades, because gravity pushes downward evenly through the structure. Earthquakes change the direction of force entirely. Instead of simply carrying weight vertically, the building suddenly must resist violent sideways acceleration. And sideways forces expose weaknesses human intuition often misses. Engineers eventually realized that earthquake survival depends not only on overall strength, but on consistency. Forces need clear, continuous paths through the structure. If one floor behaves dramatically differently from the others, stress begins concentrating there during shaking. In a sense, the building stops moving as one unified system. The weak level becomes a hinge point where deformation grows uncontrollably. Some researchers compare it to bending a stick repeatedly at the same spot until it snaps. The motion itself may not destroy the structure immediately, but concentrated stress eventually overwhelms the vulnerable section. Yet soft-story problems are not limited to earthquakes alone. Similar principles appear throughout structural engineering whenever loads become unevenly distributed. Bridges, towers, and even aircraft can experience dangerous failures when forces concentrate unexpectedly in weaker regions. Earthquakes simply expose these vulnerabilities with brutal speed. And as cities grew denser throughout the 20th century, architectural trends unintentionally increased the problem. Open ground floors became economically attractive in urban areas because they maximized parking and commercial space. Apartment complexes with large garage openings spread across parts of California. Hotels and office buildings favored wide entrance areas with minimal walls. In some cities, zoning rules and market demands quietly encouraged designs that later proved dangerous under seismic conditions. This created a troubling gap between architectural convenience and structural resilience. The very features people found attractive in modern buildings sometimes increased earthquake vulnerability dramatically. After major earthquakes exposed these risks, engineers began retrofitting older structures in enormous numbers. Retrofitting soft-story buildings often involves adding steel braces, reinforced concrete walls, or moment-resisting frames to strengthen vulnerable floors. In cities like San Francisco and Los Angeles, governments eventually passed laws requiring many older buildings to undergo seismic upgrades. The process can be expensive, disruptive, and politically controversial because thousands of structures may need reinforcement simultaneously. Some property owners resist retrofits due to cost. Others fear revealing vulnerabilities could reduce property value. Yet engineers warn that waiting until after a major earthquake may carry far greater consequences. This tension reveals something uncomfortable about modern infrastructure. Cities are filled with hidden structural assumptions most people never think about until disaster forces them into view. And earthquakes have a way of exposing those assumptions mercilessly. Another unsettling aspect of soft-story collapse involves timing. Buildings rarely fail the instant shaking begins. In many cases, damage accumulates progressively during the earthquake itself. Columns crack internally. Reinforcement bars deform. Connections weaken under repeated stress reversals. To occupants inside, the building may feel terrifying, but still stable. Then, suddenly, one critical component reaches its limit. Collapse can unfold in seconds after the structure has already survived much of the shaking. This delayed failure creates an eerie psychological effect in earthquake footage, because the moment of destruction often feels disconnected from the original force that caused it. The building appears to hesitate before gravity finally takes control. Engineers studying these collapses often describe them as cascading failures. One structural weakness triggers another. Loads redistribute unpredictably. Once enough critical elements fail, the remaining structure can no longer support itself, and gravity becomes unstoppable. In some pancake collapses, upper floors remain partially intact, even as they crush lower stories beneath them. This has led to debates among engineers about how best to design buildings for progressive collapse resistance. Some modern structures include additional redundancy specifically intended to prevent localized failures from spreading catastrophically through the rest of the building. The idea is simple in theory, but incredibly difficult in practice. A structure must not only survive the initial earthquake forces, but also maintain enough internal stability to avoid chain reactions if individual components fail. This complexity explains why earthquake engineering increasingly focuses on system behavior rather than isolated strength. Buildings are treated less like static objects and more like interconnected networks, where every part influences the others during stress. There is also a deeper psychological reason soft story collapses disturb people so intensely. Humans instinctively trust the ground floor of a building. It feels permanent because it connects directly to the earth. But soft story failures reverse that expectation completely. The weakest part of the structure often exists at the very base, supporting everything above it. That inversion creates a disturbing image. Entire towers depending on a few vulnerable columns hidden behind parking spaces or storefront glass. Some engineers argue that earthquakes reveal uncomfortable truths about urban priorities. In many cities, economic efficiency, aesthetics, and convenience quietly shaped architecture more strongly than rare catastrophic risk. Open commercial spaces generated revenue. Spacious garages attracted tenants. Large windows created appealing designs. Earthquake vulnerability remained mostly invisible until disaster struck. And because severe earthquakes may occur only once every few decades in certain regions, societies often drift toward forgetting older lessons. Building codes improve after catastrophes, but over time, memories fade, budgets tighten, and pressure for faster development returns. This cycle has repeated throughout history in earthquake-prone civilizations around the world. Yet there is another strange layer to the story. Not all soft story buildings collapse, even during powerful earthquakes. Some survive, despite vulnerabilities researchers expected to be fatal. Others fail under conditions that appear comparatively moderate. Local soil behavior, construction quality, hidden design differences, maintenance history, and even the direction of seismic waves can influence outcomes dramatically. Earthquakes remain chaotic enough that certainty is rare. Engineers can reduce risk significantly, but they cannot eliminate unpredictability completely. Perhaps that uncertainty explains why earthquake engineering often feels less like conquering nature and more like managing probabilities within systems too complex to fully control. Modern buildings contain incredible intelligence hidden inside their design, yet the earth beneath them still behaves according to forces operating far beyond human scale. And maybe nowhere is that contrast more visible than in the soft story problem itself. A skyscraper may survive massive engineering challenges at its upper levels: wind loads, oscillation control, seismic damping, only to face catastrophic danger from a single weak floor near the ground. Sometimes, the difference between survival and collapse comes down not to the tallest part of the structure, but to the smallest imbalance hidden deep within it. And after every major earthquake, engineers return once again to the wreckage, searching for patterns, trying to understand where the next hidden weakness might already exist inside the cities humans trust every day. Every major earthquake leaves behind two cities. The first is the one visible in photographs: collapsed buildings, broken highways, smoke rising through streets filled with dust and sirens. But the second city appears later, hidden inside engineering reports, rewritten building codes, emergency meetings, and quiet changes to how future structures will be designed. That invisible city may last far longer than the rubble itself. Because modern earthquake engineering is built on a deeply uncomfortable pattern. Many of the rules protecting cities today only exist because earlier versions failed catastrophically. In a strange way, skyscrapers carry memories of past disasters inside them. Every reinforced joint, flexible frame, and seismic retrofit often traces back to a moment when something collapsed unexpectedly, and engineers had to ask why. One of the earliest shocks came in 1906 when San Francisco was struck by a massive earthquake along the San Andreas Fault. The shaking itself caused severe destruction, but the fires afterward transformed the disaster into something even worse. Water mains ruptured across the city, leaving firefighters unable to control the flames spreading block by block. Entire districts burned for days. More than half the city's population was displaced. Yet what haunted engineers afterward was not only the scale of destruction, but how little people had understood about seismic risk beforehand. At the time, many structures simply were not designed with serious earthquake forces in mind. Buildings relied heavily on unreinforced masonry, brittle materials, and assumptions about stability that earthquakes shattered almost instantly. The disaster changed how Americans viewed seismic danger along the West Coast, but the real transformation unfolded slowly over decades. Early building codes remained inconsistent and often weak by modern standards. In many cities, economic growth still moved faster than seismic caution. Then, earthquakes kept returning. Long Beach in 1933 exposed how vulnerable schools were. Hundreds of school buildings suffered severe damage, and public fear pushed California toward stronger regulations requiring seismic standards for educational structures. Engineers began realizing something crucial. Earthquake safety could not rely only on individual designers making careful decisions. Entire systems of rules had to evolve collectively because the consequences of failure affected whole cities. Yet even then, the science remained incomplete. Throughout much of the 20th century, researchers still struggled to predict how real buildings would behave under complex seismic motion. Many assumptions came from theory rather than full-scale observation. Then, nature started testing those assumptions brutally. The 1964 Alaska earthquake, one of the most powerful ever recorded in North America, revealed how dramatically soil conditions could influence destruction. Entire neighborhoods experienced ground failure as saturated soil lost strength and behaved almost like liquid. Buildings tilted, sank, or slid apart, even when their structures remained partially intact. The disaster forced engineers to pay far closer attention to local geology, rather than treating earthquakes as purely structural problems. A building could perform differently depending on what existed beneath it. This realization gradually expanded earthquake engineering beyond architecture into geology, material science, fluid dynamics, and even computer simulation. But perhaps one of the most transformative events arrived in 1995 with the Kobe earthquake in Japan. Before Kobe, many people viewed Japan as one of the world's most earthquake-prepared nations. The country had invested heavily in seismic engineering and advanced building technologies. Yet the earthquake killed thousands and destroyed or damaged enormous numbers of structures. Elevated highways collapsed dramatically. Fires spread through dense neighborhoods. Some modern buildings performed far worse than expected. For Japanese engineers, the disaster became both tragedy and revelation. Detailed investigations uncovered weaknesses in older concrete columns, insufficient reinforcement details, and vulnerabilities hidden inside designs previously considered acceptable. The earthquake exposed how dangerous complacency could become, even in technologically advanced societies. And because Japan had some of the world's most sophisticated monitoring systems, researchers collected extraordinary amounts of data from the disaster. That information reshaped engineering practices globally. After Kobe, seismic retrofits accelerated across Japan. Bridge supports were strengthened. Building codes evolved again. New research expanded into energy dissipation systems, damping technologies, and improved structural ductility. But perhaps most importantly, Kobe reinforced a difficult truth engineers had slowly been learning for decades. Surviving earthquakes was not enough. Buildings also needed to remain functional afterward. Hospitals, transportation systems, emergency centers, communication networks. Modern cities depended on infrastructure continuity during disasters. Structural survival alone no longer defined success. Another major turning point arrived during the 2011 Tohoku earthquake and tsunami. The earthquake itself generated extraordinary shaking across parts of Japan, but the tsunami that followed revealed how interconnected modern risk had become. Seawalls were overwhelmed. Entire towns vanished beneath water. And at Fukushima Daiichi, cascading failures inside the nuclear power plant triggered one of the most serious nuclear accidents in modern history. Engineers studying the disaster afterward confronted a haunting possibility. Some systems had technically survived the earthquake they were designed for, yet failed because the larger chain of consequences exceeded expectations. The distinction mattered enormously. Modern infrastructure exists inside networks of dependency. Power systems depend on transportation. Hospitals depend on electricity and water. Communication depends on stable infrastructure. A disaster large enough can overwhelm assumptions built into multiple systems simultaneously. Some researchers argue this represents one of the defining challenges of 21st century engineering. Individual buildings may become safer while cities themselves remain vulnerable through interconnected complexity. Chile's 2010 earthquake offered another revealing contrast. Despite being one of the strongest earthquakes ever recorded, many modern buildings in Chile performed surprisingly well compared to older disasters elsewhere. Strict seismic codes and decades of engineering improvements likely contributed significantly to reducing widespread catastrophic collapse. Yet even there, failures still occurred. Some structures experienced severe damage due to design flaws, construction shortcuts, or unexpected soil behavior. Engineers afterward emphasized an important point often misunderstood by the public. Building codes do not guarantee zero damage. In most cases, they aim primarily to prevent catastrophic collapse and mass loss of life. A structure may survive while still requiring expensive repairs or demolition afterward. This creates a subtle but critical distinction between life safety and operational continuity. And as skyscrapers grow taller and cities denser, that distinction becomes increasingly important economically and socially. One reason modern earthquake engineering evolves constantly is because every major earthquake produces new data capable of overturning older assumptions. Instrumented buildings now contain sensors measuring acceleration, displacement, torsion, and structural response during real seismic events. Engineers compare predicted behavior against actual performance afterward, searching for mismatches. Sometimes, small details matter enormously. Weld configurations once considered safe later prove vulnerable. Reinforcement spacing changes after unexpected cracking patterns appear. Certain structural systems perform better under long-duration shaking than researchers anticipated. In many ways, earthquake engineering resembles an endless conversation between human design and geological reality. The Earth keeps asking questions through disaster. Engineers respond by rewriting the rules. Then, another earthquake arrives years later and asks different questions nobody fully anticipated. This process has become increasingly dependent on simulation technology. Modern earthquake laboratories can recreate seismic motion using gigantic shake tables capable of moving full-scale buildings violently in multiple directions. Watching these experiments feels almost surreal. Entire apartment complexes, bridges, or concrete towers shake inside laboratories, while cameras and sensors record every fracture, vibration, and deformation. Some structures survive, others collapse, intentionally, so researchers can study exactly how failure spreads. Japan operates some of the world's largest earthquake simulation facilities, where full-scale buildings have been tested to destruction under highly controlled conditions. These experiments revealed something profoundly important. Real buildings often behave more unpredictably than simplified theoretical models suggested. Small construction details can dramatically alter outcomes. Non-structural elements like ceilings, piping, and facades sometimes create unexpected hazards, even when the main structure survives. Human behavior during earthquakes also matters more than engineers once assumed. Evacuation patterns, panic responses, and infrastructure disruptions shape survival alongside structural design itself. Increasingly, earthquake resilience is viewed not as a single engineering problem, but as an entire ecosystem of interacting systems. Yet, despite all these advances, uncertainty never disappears completely. Some seismic zones remain poorly understood. Rare megaquakes may exceed historical records. Soil behavior can become chaotic under extreme motion. Even cutting-edge computer models depend on assumptions about future earthquakes humans have never directly observed. Certain researchers worry modern societies may still underestimate low-probability but catastrophic scenarios. Others argue current engineering already provides remarkable protection compared to earlier eras. The debate itself reflects a deeper truth. Earthquake safety is not a finished achievement. It is a constantly moving target, shaped by evolving science, economics, politics, and memory. And memory may be the most fragile part of all. After major disasters, societies often invest heavily in safety improvements, while fear remains fresh. Over time, however, pressure for cheaper construction, rapid development, and regulatory flexibility returns. Buildings age. Retrofitting becomes expensive. Political priorities shift. Earthquakes occur infrequently enough in many regions that entire generations may grow up without experiencing one directly. This creates a dangerous cycle where lessons purchased through tragedy slowly fade until another disaster forces them back into public consciousness. In that sense, building codes are not merely technical documents. They are historical records written in structural language. Hidden inside every seismic regulation is usually a story about something that once failed catastrophically. A collapsed bridge, a cracked hospital, a fallen apartment tower, a fire that spread because water pipes ruptured beneath the streets. Modern cities often appear calm and permanent on the surface, but beneath that appearance lies a vast archive of remembered destruction shaping how engineers design the future. And perhaps that is why earthquake-resistant architecture feels so strangely human. It evolves through mistakes, revisions, uncertainty, and adaptation, rather than absolute mastery. Every skyscraper standing today carries fragments of older disasters inside its design. But even with all these lessons, one disturbing question still remains. What happens when an earthquake arrives that exceeds everything engineers prepared for? There is an uncomfortable sentence many earthquake engineers avoid saying too casually in public, even though most of them understand it deeply. No building on Earth is truly earthquake-proof. The phrase sounds reassuring in advertisements and headlines, but the reality beneath it is far more uncertain. Modern skyscrapers can survive extraordinary forces. Cities like Tokyo, San Francisco, and Taipei contain some of the most advanced seismic engineering systems humans have ever created. Towers bend without breaking. Foundations slide on giant isolators. Hidden dampers counteract motion high above the streets. Yet, behind all of that technology remains a quiet acknowledgement that earthquakes themselves do not follow human expectations. And somewhere beneath the confidence of modern engineering lies a question that keeps returning after every major disaster. What happens when the earthquake becomes larger, stranger, or longer than the systems designed to survive it? The frightening part is that Earth has already produced earthquakes powerful enough to challenge almost anything humans currently build. In 1960, southern Chile experienced the largest earthquake ever instrumentally recorded, estimated at magnitude 9.5. Entire cities were devastated. Landslides buried communities. Tsunamis crossed the Pacific Ocean and reached places as distant as Japan and Hawaii. The planet itself rang like a bell afterward, vibrating subtly for days. Scientists later realized that megaquakes of this scale release energy so immense it becomes difficult to compare them to ordinary human experience. The rupture zone stretched for hundreds of miles. Sections of coastline permanently shifted elevation. Some regions dropped, while others rose. In places, forests died because the land sank low enough for salt water to flood inward permanently. Earthquakes at this scale stop feeling like local disasters and begin behaving more like temporary rearrangements of geography itself. And perhaps the most unsettling detail is that many major fault systems around the world remain capable of producing similar events again. Along the western coast of North America lies the Cascadia subduction zone. a massive fault stretching from Northern California to British Columbia. For years, many people underestimated the danger because the region had not experienced a giant earthquake in modern recorded history. But geological evidence eventually revealed something deeply unsettling. In January of 1700, Cascadia likely produced a massive megathrust earthquake, powerful enough to generate a tsunami that crossed the Pacific and struck Japan. Coastal forests in the Pacific Northwest still contain eerie remnants of that event. Ghost forests, where trees suddenly died after the land dropped and seawater flooded inland. Sediment layers buried beneath marshes preserve repeating signs of ancient tsunamis occurring over thousands of years. Scientists now believe Cascadia is not quiet because it is safe. It may simply be between cycles. That realization transformed how researchers think about earthquake risk. Human memory is incredibly short compared to geological time. Entire civilizations can rise and fall between major seismic events. Modern cities sometimes exist atop faults whose full behavior humans have never directly witnessed. This creates one of the most difficult problems in earthquake engineering. Buildings are designed using probabilities based on historical records, geological evidence, and simulations. But the Earth occasionally produces events beyond recent human experience. Some researchers worry that truly extreme earthquakes may expose vulnerabilities modern societies have not fully imagined yet. Not necessarily because engineers lack skill, but because certain combinations of conditions become almost impossible to predict perfectly. Magnitude alone is not the only danger. In fact, some experts argue that the character of an earthquake matters more than its size. Duration can become catastrophic. Frequency content matters enormously. Soil behavior may amplify shaking unpredictably. Near-fault pulse effects can produce violent bursts of motion capable of overwhelming structures designed for more conventional shaking patterns. In some earthquakes, buildings survive the initial movement only to weaken progressively during prolonged oscillation lasting several minutes. Modern skyscrapers often handle short bursts of force surprisingly well, but long-duration shaking introduces exhaustion into the structure itself. Steel connections deform repeatedly, dampers heat up, concrete cracks spread incrementally. Energy accumulates through thousands of cycles. The building may survive technically while still suffering severe internal damage, difficult to detect immediately afterward. Mexico City demonstrated another strange danger repeatedly throughout its history. The city sits partly atop ancient lakebed sediments, capable of amplifying certain seismic frequencies dramatically. Earthquakes originating hundreds of miles away can become unexpectedly destructive because the soft ground traps and magnifies long-period waves. In some cases, taller buildings experience stronger motion than shorter ones because their natural frequencies align with the amplified seismic waves moving through the basin beneath the city. This means the danger is not simply the earthquake itself, but the interaction between the earthquake, local geology, and the structure above. A building performing well in one location might behave very differently elsewhere under similar shaking. Then there is the terrifying phenomenon known as soil liquefaction. During intense shaking, water-saturated sediments can temporarily lose strength and begin behaving almost like liquid. Buildings may tilt, sink, or slide sideways, even if their structures remain partially intact. Roads ripple, underground pipes rupture, foundations lose stability beneath them. During the 1964 Niigata earthquake in Japan, entire apartment buildings tipped sideways while remaining remarkably intact structurally. The images looked surreal. Large buildings leaning at impossible angles, almost like ships capsizing in slow motion. In some cases, engineers later determined the buildings themselves had not failed catastrophically at all. The ground beneath them had simply stopped behaving like solid earth. This possibility deeply complicates the idea of earthquake-proof construction, because even advanced structural systems depend ultimately on stable foundations, and the earth does not always cooperate. Another disturbing challenge involves cascading disasters. Large earthquakes rarely remain isolated events. Tsunamis, fires, landslides, dam failures, hazardous material releases, and infrastructure collapse often follow. In dense modern cities, interconnected systems create new vulnerabilities previous generations never faced. Electrical grids depend on communication networks. Water systems depend on power. Hospitals rely on transportation routes remaining functional. One severe earthquake can trigger simultaneous failures across multiple systems, faster than emergency response networks can adapt. Some researchers argue that modern cities are paradoxically both more resilient and more fragile than earlier civilizations. Individual buildings may survive better, but urban systems themselves have become vastly more interconnected and therefore capable of cascading failure under extreme stress. Fukushima became one of the clearest examples of this complexity. The nuclear reactors initially survived the earthquake itself better than many feared. But the tsunami disabled critical cooling systems, leading to a disaster shaped not by a single failure, but by overlapping consequences exceeding design assumptions. This exposed another uncomfortable truth about engineering. Systems are usually designed around scenarios considered plausible or economically reasonable, but nature does not operate according to human budgeting logic. Sometimes, reality combines multiple extreme events simultaneously, and perhaps nowhere does uncertainty become more psychologically unsettling than in discussions about the big one along California's San Andreas Fault. The phrase itself almost sounds mythical now, repeated so often it risks losing emotional impact. Yet scientists remain confident that major earthquakes will continue occurring along California's fault systems. The exact timing remains impossible to predict precisely. Some sections appear locked and accumulating strain. Others behave more unpredictably. Modern California contains some of the strictest seismic codes in the world, and many experts believe contemporary skyscrapers would perform far better than older structures under a major event. But even optimistic scenarios involve enormous disruption. Fires, infrastructure failures, water shortages, transportation paralysis, economic shock. Earthquake engineering has advanced remarkably, but modern cities remain deeply dependent on continuous systems vulnerable to interruption. There is also a growing debate about whether climate-related changes could influence certain geological hazards indirectly through groundwater shifts, reservoir pressures, or changing stress conditions in specific regions. The science remains incomplete and controversial in places, but it reflects a broader reality. Earth systems are interconnected in ways humans may not fully understand yet. The deeper scientists study geology, the more they uncover layers of complexity operating beneath civilization quietly all the time. Faults interact. Stress transfers between regions. Tiny shifts underground can alter probabilities elsewhere. In some cases, one earthquake appears to increase the likelihood of another nearby by redistributing tectonic stress. The planet behaves less like a stable platform and more like a constantly evolving mechanical system humans only partially comprehend. And perhaps that is why the question of whether technology can become useless during a sufficiently large earthquake remains so haunting. It forces humans to confront the limits of prediction itself. Modern engineering is extraordinary, precisely because it works so often against forces once considered impossible to survive. But earthquake-resistant design is fundamentally a probabilistic science, not a promise of invincibility. Buildings are designed to reduce risk dramatically, protect life, and improve resilience. Yet every engineer understands there are always assumptions beneath the calculations. Assumptions about magnitude, duration, frequency, soil behavior, material performance, and countless variables nature may not fully respect. That does not mean technology is futile. In many cities, seismic engineering has already saved countless lives compared to older eras. Entire skylines now survive earthquakes that would once have destroyed them. But the existence of megaquakes reminds humanity of something deeper. Civilization does not stand outside nature, controlling it completely. It exists inside dynamic planetary systems, still capable of overwhelming even the most advanced structures humans can build. And strangely, some of the most important lessons about surviving those forces may not come from technology alone at all. Because long before skyscrapers existed, nature had already spent millions of years solving problems involving flexibility, balance, energy dissipation, and survival under constant environmental stress. And engineers eventually began realizing that some of the smartest earthquake-resistant designs on Earth might already exist quietly inside the natural world itself. Long before humans understood tectonic plates, resonance, or seismic waves, nature had already been solving structural problems for millions of years. Forests survived violent storms without snapping apart. Bones carried enormous loads while remaining surprisingly light. Trees flexed under pressure instead of resisting it rigidly. Even tiny insect nests contained ventilation systems and load distribution patterns sophisticated enough to confuse modern engineers when they first studied them closely. And at some point, researchers began noticing something strange hidden inside many earthquake-resistant designs. The closer engineers looked at nature, the more they realized Earth's most resilient systems almost never depended on brute strength alone. Survival usually came from flexibility, balance, redundancy, and the ability to absorb energy without catastrophic failure. In other words, many of the same principles modern skyscrapers rely on today were already quietly operating in the natural world all around us. One of the simplest examples appears in bamboo forests. During strong winds, bamboo bends dramatically, while many heavier trees crack or uproot entirely. At first glance, bamboo seems fragile because it is hollow and relatively lightweight. But that apparent weakness hides extraordinary structural intelligence. Bamboo fibers distribute stress efficiently along the length of the stalk, allowing the plant to flex under pressure without breaking easily. Its segmented structure also helps prevent cracks from spreading catastrophically. Engineers studying seismic design became fascinated by these properties because earthquakes create a similar challenge. Buildings must absorb movement without snapping under concentrated stress. Some modern structural systems intentionally mimic this philosophy by allowing controlled deformation throughout the frame rather than forcing complete rigidity. Certain earthquake-resistant materials now incorporate layered flexibility, inspired partly by biological structures capable of dispersing force gradually across interconnected systems. But perhaps the most fascinating lessons came not from plants, but from ancient architecture itself. In Japan, some wooden pagodas have survived centuries of earthquakes despite being built long before modern engineering science existed. Many of these structures rise multiple stories high with remarkable elegance and flexibility. At first, researchers struggled to understand why they performed so well during seismic events compared to some heavier stone or masonry buildings. Then, engineers began studying one particular feature hidden inside traditional pagoda construction: a central wooden column called the shimbashira. The exact role of the shimbashira remains debated among historians and structural researchers, partly because ancient builders did not leave behind modern engineering explanations. But many experts believe the central column contributes significantly to the pagoda's earthquake resistance. Rather than rigidly fixing every floor together, parts of the structure can move somewhat independently during seismic shaking. The building dissipates energy through internal motion instead of concentrating stress into brittle failure points. Some researchers compare the effect to a suspended pendulum, helping stabilize the structure dynamically. Others emphasize how flexible wooden joints and layered construction absorb vibration gradually. What makes these pagodas especially remarkable is that many survived earthquakes that destroyed far newer buildings nearby over the centuries. The structures reveal a recurring pattern. Nature seems to favor repeatedly. Systems capable of movement often survive better than systems obsessed with rigidity. Wood itself plays a surprisingly important role in this story. Unlike brittle masonry, wood possesses natural flexibility and relatively low mass. During earthquakes, lighter structures generally experience lower inertial forces because there is simply less mass resisting motion. Traditional Japanese architecture often relied on interlocking wooden components, capable of shifting slightly under stress, rather than cracking immediately. In some historical earthquakes, entire wooden districts survived better than heavier stone construction, despite appearing less strong in the conventional sense. Modern engineers studying timber construction have returned to many of these ideas with growing interest. Engineered wood products, like cross-laminated timber, now allow surprisingly tall buildings while maintaining flexibility and reduced weight compared to traditional concrete systems. Some researchers believe timber skyscrapers may eventually play a larger role in seismic regions, partly because their lower mass reduces earthquake forces significantly. Once again, the deeper engineers study resilience, the more they encounter principles already embedded in natural materials. Another source of inspiration emerged from trees themselves, particularly root systems. A tree survives storms not only because of the trunk above ground, but because of how forces distribute below the surface. Root networks spread loads outward through interconnected pathways rather than concentrating all stress in one rigid point. Some modern foundation systems apply similar logic by distributing seismic loads more dynamically across structures instead of relying solely on fixed resistance. Certain advanced base isolation systems even resemble biological shock absorbers in the way they manage movement gradually. Biomimicry, the practice of drawing engineering inspiration from nature, has become increasingly influential in architecture because biological systems evolved under environmental stress for millions of years. Nature rarely wastes energy fighting forces directly if flexibility and adaptation work better. Even the shape of some modern skyscrapers reflects lessons borrowed indirectly from natural forms. Twisting towers, tapered profiles, and aerodynamic surfaces often mimic patterns, reducing turbulence and distributing force more efficiently. Engineers learned that rigid geometric simplicity sometimes performs worse under dynamic conditions than shapes capable of disrupting harmful oscillations naturally. Insects provided another surprising source of insight. Researchers studying termite mounds discovered complex internal ventilation systems regulating temperature and airflow with astonishing efficiency. While this relates more directly to climate control than earthquakes, it reinforced a broader realization among architects. Natural systems frequently solve multiple environmental problems simultaneously through integrated design rather than isolated solutions. Earthquake resistance increasingly follows this philosophy as well. Buildings now combine flexibility, damping, energy dissipation, aerodynamic shaping, and adaptive materials into interconnected systems rather than relying on one single defensive strategy. Some researchers even explore whether future structures could behave more like living organisms, continuously adjusting themselves in response to changing environmental forces. There are already experimental materials capable of altering stiffness under certain conditions or healing small cracks automatically over time. The line between architecture and biological adaptation continues blurring slowly. Yet perhaps the most profound lesson nature taught earthquake engineers is philosophical rather than mechanical. Nature almost never seeks absolute permanence. Mountains erode, trees bend, bones remodel themselves under stress. Ecosystems adapt continuously rather than remaining fixed forever. Human architecture historically pursued the opposite ideal: permanence through rigidity, dominance over environmental forces, structures appearing immovable against time itself. Earthquakes exposed the limits of that mindset repeatedly, The buildings surviving best were often not the strongest looking, but the most adaptable. This shift transformed how engineers think about resilience. Modern seismic design increasingly accepts movement, controlled damage, and dynamic response as unavoidable parts of survival. In some ways, buildings became less like monuments and more like participants in their environments. There is something strangely humbling about that realization. Humanity often imagines advanced technology as separate from nature, yet some of the smartest engineering solutions emerge precisely when humans stop fighting natural principles and begin learning from them instead. Even the concept of resonance, one of the most dangerous phenomena in earthquakes, exists throughout biology. Muscles, tendons, bones, and circulatory systems all operate through carefully balanced mechanical relationships involving vibration, energy transfer, and flexibility. Biological structures survive repeated stress not by eliminating force entirely, but by distributing it intelligently across systems capable of adaptation and repair. Some earthquake engineers now view cities similarly, not as rigid collections of isolated buildings, but as living networks requiring flexibility, redundancy, and recovery capacity across multiple scales simultaneously. Still, nature does not offer perfect answers. Trees eventually break. Ecosystems collapse under sufficient stress. Biological systems evolved through survival probabilities rather than guarantees. Engineers, borrowing ideas from nature, must still adapt them carefully to human materials, economics, and urban realities. Some biomimetic concepts remain experimental or controversial. Others work beautifully in theory, but become difficult to implement at city scale. Yet, the influence of nature on seismic engineering continues growing because the parallels remain difficult to ignore. Earth itself is a dynamic system, shaped by motion, pressure, vibration, and constant change. Structures surviving within that environment may ultimately need to behave less like rigid objects and more like flexible processes. Perhaps that explains why the future of earthquake-resistant architecture increasingly feels alive in subtle ways. Buildings sway intentionally. Foundations slide. Dampers move independently inside towers. Materials flex, absorb, and recover. Hidden systems respond dynamically to stress, almost like reflexes inside a body. The skyline itself begins behaving less like frozen stone and more like a giant mechanical ecosystem quietly adapting to the restless planet beneath it. And as engineers continue borrowing lessons from forests, bones, roots, shells, and ancient wooden temples, another possibility begins emerging. One even stranger than the idea of buildings that bend. What if future cities eventually become structures capable of sensing earthquakes, responding automatically, and changing their behavior in real time before humans even realize danger has begun? Late at night, in parts of Japan, California, and Taiwan, thousands of buildings are already listening to the earth. Hidden inside walls, foundations, bridges, subway tunnels, and skyscrapers are networks of sensors constantly measuring vibration so small humans cannot feel it. Most of the time, the systems remain silent. Tiny motions pass through the ground every day. Trucks moving through distant streets, ocean waves interacting with coastlines, subtle geological shifts deep underground. Modern cities quietly vibrate all the time, but engineers increasingly believe those invisible signals may become part of something far larger in the future. Cities capable of reacting to earthquakes almost like living organisms before people even realize danger has begun. That idea once sounded close to science fiction. For most of human history, earthquakes arrived without warning and left destruction behind faster than civilizations could respond. But technology is slowly changing the relationship between cities and seismic risk, not by eliminating earthquakes, but by making urban systems more adaptive, flexible, and aware. In some places, the future may not involve defeating earthquakes at all. It may involve learning how entire cities can move with them. One of the most important breakthroughs already exists today in early warning systems. Earthquakes release different types of seismic waves, and some travel faster than others. Primary waves, called P waves, move quickly through the ground and are often less destructive. More dangerous secondary waves usually arrive afterward. Modern sensor networks can sometimes detect the faster waves first and send alerts before the strongest shaking begins. The warning may last only seconds, occasionally less than that. But even a few seconds can matter enormously. Trains can slow down automatically. Elevators can stop at safe floors. Gas lines may shut off. Surgeons can pause delicate procedures. School children can take cover. Entire transportation systems may react before most humans consciously understand an earthquake has started. In Japan, this technology already functions on a national scale. Phones emit alerts moments before shaking arrives. Bullet trains automatically engage emergency braking systems. Some factories pause hazardous operations instantly. The system does not predict earthquakes in advance in the traditional sense. Scientists still cannot reliably forecast the exact time and location of major seismic events. Instead, the warning network responds to the earthquake already happening underground, faster than human perception can. That subtle distinction matters. The Earth still controls the event. Humans are simply becoming quicker at reacting to it. But researchers are now pushing towards something even more ambitious. Instead of buildings merely surviving earthquakes, future structures may continuously monitor their own internal condition in real time. Some modern skyscrapers already contain hundreds or even thousands of sensors measuring acceleration, stress, vibration, temperature, and structural movement. Engineers can track how forces move through the building during storms and earthquakes, almost like doctors monitoring a patient's heartbeat. Over time, artificial intelligence systems may analyze these patterns constantly, identifying tiny structural changes long before visible damage appears. Hairline cracks inside concrete, fatigue in steel joints, slight shifts in resonance behavior. Future buildings might not wait for inspections after earthquakes, because they could already know where they are weak. In some experimental systems, structures essentially create digital versions of themselves, constantly updated computer models, sometimes called digital twins. These virtual replicas receive live sensor data from the real building and simulate how the structure behaves under stress. During future earthquakes, engineers may watch damage evolve inside digital models in real time, while emergency systems respond automatically. Entire buildings could potentially adjust damping systems, redistribute loads, or isolate vulnerable components dynamically as shaking unfolds. The architecture begins behaving less like passive construction and more like an active participant in its own survival. Some researchers even imagine skyscrapers eventually becoming semi-autonomous systems capable of making limited structural decisions independently during extreme events. Materials themselves are changing too. One of the most intriguing developments involves self-healing concrete. Traditional concrete cracks under stress, and once water enters those cracks, corrosion and long-term deterioration can accelerate. Self-healing concrete attempts to address this problem using materials capable of sealing small fractures automatically over time. Certain versions contain bacteria that activate when water enters cracks, producing limestone that gradually fills damaged areas. Other experimental materials use embedded polymers or chemical reactions to repair microfractures internally. The technology remains evolving and expensive in many cases, but it reflects a broader shift in engineering philosophy. Future buildings may no longer behave like static objects slowly degrading over decades. They could become systems capable of adaptation, monitoring, and partial self-repair. Another major transformation may come from timber skyscrapers. For years, the idea of tall wooden buildings sounded unrealistic to many people because wood carried associations with fire risk and fragility. But engineered timber products have changed that perception dramatically. Cross-laminated timber combines layers of wood into large structural panels with remarkable strength-to-weight ratios. Compared to heavy concrete structures, timber buildings often experience lower seismic forces simply because they contain less mass resisting acceleration. Wood also possesses natural flexibility and energy absorption characteristics beneficial during earthquakes. Some architects and engineers believe future seismic cities may rely increasingly on hybrid structures combining steel, concrete, and engineered timber in ways balancing strength, flexibility, sustainability, and resilience. If that happens, future skylines may look modern while quietly reconnecting with ancient principles hidden inside traditional wooden architecture humans used centuries ago. Yet perhaps the strangest possibility involves buildings capable of physically changing behavior during earthquakes. Researchers are exploring adaptive structural systems using controllable dampers, smart materials, and semi-active technologies that alter stiffness or energy dissipation dynamically based on real-time conditions. Some systems already exist in limited forms. Certain dampers use magnetoheliological fluids, liquids containing tiny metallic particles that change viscosity when exposed to magnetic fields. During seismic motion, computers can adjust the fluid's resistance almost instantly, altering how the building absorbs energy. Other experimental concepts involve structures with movable masses, adjustable bracing systems, or flexible components capable of responding differently depending on the type of motion occurring. In essence, future buildings might not possess one fixed structural personality. They could shift behavior as conditions change. This begins sounding remarkably biological, and perhaps that is no coincidence. The deeper engineers study resilience, the more architecture starts resembling living systems. There is also growing interest in how entire neighborhoods and infrastructure networks respond collectively to earthquakes, rather than focusing solely on individual buildings. Smart electrical grids may isolate damaged sections automatically to prevent cascading failures. Water systems could reroute flow dynamically around ruptured pipelines. Autonomous drones might inspect bridges and high-rises immediately after earthquakes, faster than human teams could reach them. Artificial intelligence may help emergency services prioritize rescues by analyzing sensor data from thousands of structures simultaneously. Some urban planners envision future cities functioning almost like distributed organisms, capable of absorbing damage locally while maintaining broader functionality across the system. Of course, not everyone views this future optimistically. Increasing technological complexity introduces new vulnerabilities as well. Highly interconnected systems may depend heavily on software, sensors, communication networks, and electricity. Cybersecurity concerns emerge. System failures could propagate unexpectedly through automated infrastructure. Some engineers warn against over-reliance on technologies humans may not fully understand under extreme conditions. Others question whether wealthy cities alone will benefit from advanced seismic systems, while poorer regions remain vulnerable to older forms of destruction. Earthquake resilience increasingly intersects with economics, politics, and inequality as much as engineering itself. There is also the unresolved reality that precise earthquake prediction remains elusive, despite decades of research. Scientists can estimate probabilities, identify dangerous fault zones, and study precursor signals, but reliably forecasting exactly when and where a major earthquake will strike remains one of the most difficult challenges in geophysics. Some researchers continue exploring possible warning indicators involving groundwater chemistry, electromagnetic anomalies, slow slip events, or unusual animal behavior. But no universally accepted predictive system exists today. This uncertainty continues shaping everything about earthquake engineering. Cities cannot wait for perfect prediction. They must prepare continuously for events that may happen tomorrow or decades from now. And maybe that uncertainty is what makes the future of earthquake-resistant cities feel so psychologically different from older visions of technological progress. Earlier generations often imagined the future as humanity gaining increasing control over nature. But seismic engineering evolved toward a more complicated relationship. Modern cities are not learning how to stop earthquakes. They are learning how to adapt, flex, absorb, recover, and survive within a restless geological world. The philosophy quietly shifted from domination toward coexistence. In some ways, future earthquake-resistant cities may look less like fortresses standing against nature and more like ecosystems designed to move with it intelligently. And perhaps the most remarkable part is how invisible much of this transformation already is. People walk through train stations protected by hidden seismic isolators without noticing. They work inside towers, constantly adjusting tiny damping systems above their heads. They live in cities where algorithms monitor underground vibrations all day and night. civilization increasingly rests on silent systems designed around the assumption that the ground beneath us is never truly still. Yet, despite all these advances, one truth remains strangely unchanged from the beginning. Earthquakes continue reminding humanity that permanence is partly an illusion. Skyscrapers sway, foundations slide, steel bends, entire cities adapt because the planet itself is alive beneath them. And maybe the real future of earthquake engineering is not a world where humans finally conquer seismic forces completely, but a world where cities become wise enough to survive by accepting something older civilizations learned long ago. The Earth is always moving, whether humans feel it or not. Thanks for spending this time with me tonight. If you enjoyed exploring the hidden systems behind earthquakes and skyscrapers, don't forget to subscribe and leave a like. Sleep well, and I'll see you in the next journey through the systems shaping our world.